If all you need from a gearbox is more torque and less speed, then a simple set of gears is probably the way to go. But if you're like me and just absolutely insist on having 5-axis CNC machining capabilities in your back shed, you're probably going to want a solution that takes care of the pesky backlash inherent to any toothed gear reduction system. Those solutions cost money, a lot of money. So I designed and built my own zero-backlash cycloidal drive from scratch. But you and I both know it didn't start out that way. What the f? Just quickly, this video is less about how you yourself can build a cycloidal drive, and more about an overconfident nerd spending over 200 hours charging head first at an extremely complex and multifaceted exercise in technical design and execution. If you want to actually build one of the things, I've put all my sources in the description below. It's me, I'm the nerd. Back to the video. Now, as far as I know, there are 2 existing technologies that do a great job of solving the particular sort of slop that we know as backlash straight from the factory. Strain wave gearboxes are the first, and use a flexible inner spline ring and an elliptical bearing to work their magic. The bearing forces the inner ring into contact with the housing, which has 2 extra splines. When the bearing is rotated, the splines act as wedges, and the inner ring is slowly rotated. The simplicity of this mechanism is great on paper, but the material requirements for the flexible spline ring, along with other complexities in the machining, made my head hurt. So it was on to plan B. While it might look and be more complicated, the basic principle of a cycloidal drive is pretty similar. An eccentric shaft pushes the cycloidal disc against a ring of rollers, and because of the mismatched ratio of lobes to rollers, the disc slowly rotates, driving the output pins. Also, unless you're putting together the most overbuilt magic wand in history, it's a good idea to add a second disc, offset 180 degrees, to balance out any vibrations. Now, I'm not an engineer, but I am learning, and your comments are a great help. This one in particular helped me realize that by using commonly available dowel pins as the rollers, all I'd have to take care of is the cycloidal discs and the housing, which seemed reasonable enough at the time. So a cycloidal drive it was. When it comes to designing a cycloidal disc, the unfortunate reality is you can't just go slapping a bunch of lobes on a circle, all willy-nilly. Thankfully, the name offers a very helpful clue as to the specific shape required, a disc. But more specifically, a cycloidal disc. Notice I said clue, because what we actually want, and really this should be obvious, is a trochoid. I dropped out of maths as soon as I could, so I'm as confused by all this as you are. But it's enough to say that if you wrap a cycloid around a circle, an epicycloid if you will, like we're so ambitiously planning, you get a shape with these sharp transitions. And while that would do the trick, I have it on good authority that using a trochoid wrapped around a circle, an epitrochoid if you will, results in much smoother operation. If you like smooth operation, you should like the video, and if you subscribe, I'll know you want to see more. Once I knew what I was actually trying to draw, it was a simple matter of creating an equation-driven curve and designing a housing around it. I went with a 25:1 reduction to maintain a bit of speed on the output and keep everything a reasonable size. I'll explain what's going on with this mess of components you're looking at later on. But for now, it's enough to say that, being the perfectionist that I am, I made sure to get everything right on the first try. Alright, so maybe not on the first try, but the second try went a whole lot better. For now, we have to figure out what not to do. Once I have my design, cricket.
Shut up.
Once I had my design, it was time for me to start machining. I started off with some 25mm mild steel plate for the housing, cutting it down to roughly the right size on this poor little import bandsaw, which was certainly approaching the limits of its capacity, especially with such a fine-toothed blade. I quickly faced the stock on the lathe. Then it was on to the mill for a fairly ridiculous setup. Once it's time to move the part back over to the lathe, I'll need something to hold on to that's vaguely concentric with the roller seats. So the plan was to use the rotary table to mill the outside face, nice and circular. Yeah, I know it's a CNC mill, and I know it can move in circles. But at the time, I still had some major trust issues about its ability to move in true circles, right as I'm about to start a project that requires circularity down to the 100th of a millimeter. Go figure. But first things first, this thing needs some holes. I started off with a 3mm pilot hole because there aren't enough pairs of undies on planet Earth for me to give this machine free rein with a 7.5mm drill on 25mm plate. Then I followed up with said drill and what is definitely an 8mm reamer, and certainly not an end mill, to bring the holes to size. Except these pins are ever so slightly oversized, so it was time for the most overplayed joke on machinist YouTube. The boring part. Once I'd finished butchering the roller seats, I made use of the rotary table to surgically remove the waste material in the center of the part. And added that circular reference I mentioned earlier. The cycloidal discs were next. I was pretty sure the tolerances on all the functional features of these parts were equally critical, so I decided to make up a locating fixture that would let me machine them all in one setup. Prepping the stock was just a matter of facing both sides and drilling and boring a few holes. Then some roughing. Then I finished the holes with the boring head and the outside profile with a ramping contour. To measure my progress on the outside contour, I made up a gauge block stack that fits snugly between rollers in the housing to find my target dimension, then measured the cycloids from lobe to valley with the help of a pin. Then I could gradually reduce the stock to leave until I had what I thought was a good fit to the housing. Take note of that sticky spot though, it'll come back to bite me later. Then it was back to the bandsaw to get rid of the corners on the roller housing to make the next step a little less painful. Over at the lathe, I switched to the 4-jaw and dialed in the part. This setup and the interrupted cuts that followed were no fun, but that wasn't enough to make me turn back. Not yet. Speaking of turning, you might have noticed a new toolpost sitting atop the compound there, which must mean it's time for a side project from the future.
The future.
Hang on, wait, where are you going? We're already here. It's the future now. Having spent more than my fair share of time using a 4-way toolpost on the lathe at work, I knew from the start that this lathe would be getting a quick change. The only thing sort of holding me back from getting one at the start was the idea that I might make one myself. And that might still happen, because this is only the cheapest example in the Allura style I could find, and it does have its issues. That being said, once I'd given it a good clean and deburr, and turned up an appropriate mounting bolt, it totally serves its purpose. Well, mostly. It only came with 4 tool holders, which meant for the rest of this project, I was using a hex key to change out tools even more than I had to with the 4-way tool post. Now there's an obvious solution to this massive pain in my ass, and that's to buy more tool holders, but I wasn't really thrilled with the options I was seeing online, both in terms of cost and the fact that I've got some unique requirements I'd like to fulfill. Now, don't worry, I'm not going to try and squeeze the entire process of making a custom set of tool holders into this video, because A, I've still got a cycloidal drive and a half to make, B, it's been done plenty of times, and C, PCBWay's done all the machining for me. You might know PCBWay as a leading manufacturer of custom printed circuit boards, but did you know they have a huge range of CNC machining services as well? From laser cutting and sheet metal bending, to mill turning and 3 and 5 axis milling. PCBWay has the CNC machining capabilities to get any side project over the line. So click the link below and get a free quote today. That must be those tool holders now. Now, not being an engineer, I didn't have much confidence in my ability to accurately measure these dovetails, let alone communicate that information through a technical drawing. So I made sure to leave a bit of meat on the files I sent to PCBWay, about 1/2 millimeter. This actually worked out perfectly, because by the time I'd scraped the tool post in, the tool holders were a perfect fit. I have to say I'm incredibly impressed with these parts. The surface finish is light years ahead of what I could have achieved, and it kinda looks like the dovetails were cut on an EDM machine. Now that's fancy. The bulk of this collection are these extended holders, based on the Aloris DA13, but with a handy twist. You see, by adding threaded holes top and bottom, I've essentially quadrupled the versatility of these holders. Then there's some fairly standard boring bar holders, and some not so standard oversized holders for those insert tools I showed earlier. I got those cutters, along with a few good chunks of stock, and this absolute unit of a drill press from a local engineering workshop that was driven out of business by the insanity of this current Sydney rental crisis. I feel I owe it to David to put these tools to good use, even if they do look a little bit ridiculous on my teeny weeny bench lathe. I haven't got enough material or patience to make up adjustment nuts for all the holders just yet. And despite lucking into this king's ransom of a hardware collection, of course I'm missing the one type of screw I need. I probably should have just let PCBWay take care of those too. Which brings us to the last chunk of 4140 in the bunch, a solid tool post mount. As you'll see later in the video, I've been having a bit of trouble with surface finish on this lathe. I'm sure a lot of you will argue that that's because I lifted the thing by the spindle and routed the bearings. But I'm not convinced, and the conventional wisdom seems to be that the compound is usually the weakest link between the tool and the workpiece. So I'm more than happy to give a solid tool post mount a shot. But before I pull this compound off the machine, and while we're here in the future, I'll give the new holders a go, cutting the taper in this tombstone blank for the finished 4th axis. And maybe I'll do a couple more. But that's enough messing about. I've still got a cycloidal drive and a half to make. Thanks again to PCBWay for sponsoring this video and helping tool up this lathe. Once I'd run a finishing pass, things got a little groovy. The idea there was to create a space for the grease to live, but the reality was that I just created a whole lot of burrs. For now, we'll just throw that on the growing pile of things that I absolutely won't be doing on the next try. Flipping the roller housing in the forejaw gave me access to the rest of its outer diameter. At this point, I had the cycloids and the housing, and that camshaft I threw together at the end of the last video. And let me tell you, this was a dangerous place to be on a project like this. I spent hours fiddling, and no small part of that was denial. You see, I wasn't quite getting the smooth cycloidal action I'd spent so long fantasizing about, and I wasn't quite sure why. Was it the crappy surface on the roller seats, or the millions of tiny burrs alongside them? Was it that the cycloids were too big, and that the outside walls weren't square? It should have been the turning point. But having already sunk quite a few hours into the machining of these parts, not to mention the time wasted fiddling with them, I resolved to see it through. You see, I had one more theory, that the discs just weren't constrained well enough, and that completing the rest of the housing would magically solve all of my issues. In hindsight, it was all of those problems, and certainly some more, that were equally to blame for that current cycloidal conception's incurable condition. So don't worry, I'm not going to spend too much more time on the rest of this failed attempt before we get to the good part. I'll just jump to the end and point out the rest of the obvious when you think about it flaws in this design. Because of the material limitations I imposed upon myself in the form of 10mm plate, I didn't have the space to mount bearings. So I'd convinced myself that a plain bearing integrated directly into the covers and preloaded by the output pins was a viable solution. But getting the pins to the right length was an absolute pain in my ass. And that was because I'd done such a good job of convincing myself that it didn't matter if things weren't exactly as they appeared on the print, as long as I could just machine them to fit later. I also didn't really have a plan for how I'd be able to actually use this thing. I knew that I did want to build the spindle separately, but I really hadn't spent any time thinking about how the two would connect. At the end of the day, all these problems come down to one root cause. I rushed the design, and left a lot of the problem solving to future me. And now I was future me, and it sucked. I definitely have a certain propensity to hold on to first tries and failed attempts, but on this occasion, I could see the continued presence of this part posthumously was only going to hold me back. There was only one place it belonged. The box of shame. So as it completed its final journey, I set off on mine. I went back to the drawing board. And this time, I spared no expense, only feeling slight remorse at pillaging the material and bearings I'd been saving for a certain second-hand lathe project, now sitting by the wayside. Trading the improvised plain bearings for made-in-Japan tapered roller bearings was a no-brainer, and should give the cycloids more than enough constraint to run true, while building everything into one package cuts down on the number of parts and opportunities for misalignment. Oh, and I remembered to put my glasses on this time, which certainly helped. The first attempt had taught me a lot, but I think the biggest and most important lesson was when to cut my losses. So when I snapped that ream 20mm and 45 minutes into the housing, I didn't even hesitate to start again, this time with a different strategy. I skipped the drilling and jumped straight to milling. This hadn't been a great option for my first attempt because of the solid core, but I was living in tube world now, baby. Following the 8mm tool with a 6, and then the boring head. Resulted in an excellent finish on the roller seats. Things were off to a great start. By this stage, I'd spent way too long suffering the pace of my itty-bitty bandsaw, nibbling at solid bar. This was just the excuse, project I needed to get a bandsaw with teeth.
What the f***?
Cada día le doy las gracias a esta vida.
Having gained the ability to cut steel like never before, my strategy for extracting the cycloids shifted from plate to bar, which in turn simplified the work holding to a humble lathe chuck. This time I actually took advantage of the fact that this is a CNC machine by running both cycloids at once.
Yo sabía que algún día llegaría. Qué alegría pasar el tiempo a tu lado. Qué alegría.
I wanted to mention I made the switch back to a manual drawbar a while ago, so I no longer fear for my life quite so much when this thing's running in the shed with me. The process of measuring and checking the discs stayed the same, but this time I made sure to take off a little more meat and not skimp on those spring passes. Once all the milling was done, I could cut them free of the stock and, using this handy step to hold on, bring them to final thickness on the lathe. Here, just a word of caution. Make sure to take note of the end of your cross slide travel. And failing that, when it power feeds into that end, definitely don't panic and throw the lever into longitudinal feed.
What the?
Luckily, the only consequence was a bit of belt slip, and after a change of socks and undies, the evidence of that brief but violent episode was wiped away in a flurry of chips.
Cada día le doy las gracias a esta vida. Tengo tanta
Back to the housing, I turned the outside diameter true to the roller seats. Added a small step that will locate the cover plate, and bored clearance for the drive plate. It was a bit nerve-wracking flipping the part because it meant it was time to tackle yet another new challenge. Cutting a precision bore to within 10 microns or so to give the tapered roller bearings somewhere cozy to live. Amazingly, I was actually almost prepared for this challenge in the lead up to building the spindle for that other old lathe. I'd stocked up on budget bore gauges and micrometers and put together my own version of Robin Renzetti's large bore lapping tool. I think it's also maybe worth a mention that I'm doing all this work on the lathe without a digital readout, which isn't a brag or an excuse, more of a cry for help. But the low speed application of these bearings sets the bar a little lower than a lathe spindle, which makes it a perfect first exercise. At least that's what I'm telling myself. I brought the bore to within 20 microns of its target dimension, which will hopefully end up being a transition fit for the bearing cup, and then I added a clearance groove at the bottom and took care of the threads for the bearing cup retaining nut. After a couple of finishing passes on the outer diameter, I moved on to lapping. This aluminium disc has an internal taper, so it expands as you tighten that nut. All you really have to do is run the lap up and down the bore, letting the part rotate every now and then to average out the influence from your hands. You'll feel when it's not cutting anymore, at which point simply expand the lap a smidge and repeat the process until you get the target dimension. Fortunately, I didn't leave quite enough material to fully polish the bore, but that's just a lesson learned and space for the glue. Time to start on that spindle. Being my first time working with 4140, it took me a while to figure out what feeds and speeds to use, but once I had them dialed in, I was breaking chips like never before, even if they were a little blue. I almost started to regret removing the safety guards, but I'm not sure they could have done much to stop the hail of burning razor blades. Seriously, these things are f***ing everywhere. I completely machined my first attempt, along with a matching nut, before I realised I'd made it too long.
Oh, come on.
And with no good way to remount it in the lathe. I started again. This offered a great opportunity to stop and actually consider how I was going to mount faceplates and fixtures to the spindle nose. I decided on a short 5-degree taper with a pick and mix of tapped holes on the face. And this time around, I remembered to cut all the radial features in one setup to guarantee concentricity. I lapped this bearing mounting surface as well, with equally uneven results. It's really hard to strike that balance between surface finish and how much time you really want to spend lapping. Both the housing and the spindle got their matching nuts. Wait, is this a nut or a bolt? And I put a taper and probably a few more holes than strictly necessary into the drive plate. I transferred the 6 inner holes to the spindle, then drilled and tapped them M3. The 6 outer holes will accept the drive pins, which are just some 8mm shoulder bolts that ended up on the wrong side of Henry VIII, and the remaining 3 will lock the bearing preload nut in place. The final piece of the puzzle was a new crankshaft to match the new cycloids. My first attempt ended up with half the required offset.
Are you kidding me?
So I made the second one twice as fast, and that seemed to do the trick. If you're wondering why I flipped the tool upside down for the second cam lobe, it's because my grooving tool looks like this. With all the parts complete, I'd love to say it was as simple as just putting everything together, but I love a good fiddle, and I was going to make damn sure that this thing was going to fit together and work before I doused all the parts in grease, Loctite and retaining compound. So only after a half dozen or so dry fits to check clearances, find the best arrangement of pins, and trigger anyone who knows anything about how clean you need to keep bearings in a precision application like this, was it time for the final assembly. The bearing cups and their spacer went in first, with a healthy coating of retaining compound. They did need a little tappy tap to get them started in the bore, but once I got them lined up, they slid in with the slightest amount of resistance. Of course, despite my many practice runs, I still managed to put this one in the wrong way around on the first try.
That's the wrong f***ing way around.
On the plus side, the panic of trying to get the thing out before it was locked in place forever really made me feel alive. At least I remembered that the front bearing cone needs to be mounted before the retaining nut is installed. Just.
God, I'm an idiot.
I lightly packed the rollers with lithium grease, put it into the housing, and locked the retaining nut in place. Flipping the whole thing over, I installed the rear cone, without retaining compound this time, as it needs to slide on the shaft for preload adjustment, and installed the preload nut. A few good taps snugged it up and took any play out of the bearings. The drive plate went in next. This O-ring will hopefully spare the bearings from any chunks that inevitably wear off the cycloids, and 6 M3 screws draw it down onto its locating taper. The 3 set screws make sure that the bearing preload nut doesn't get any funny ideas about coming loose and ruining my day. The drive pins get their bearings, and a squirt of grease on the roller seats helps to keep the 26 dowel pins in place for the installation of the cycloidal discs. The alignment necessary to get the discs in really is satisfying. A bit more grease and a quick test to make sure everything is functioning as it should means I can seal up this nightmare of an assembly once and for all. Well, at least until it stops working. The project was really starting to drag out at this point, just like the video. So for the time being, I quickly printed a motor mount for testing purposes and connected the stepper motor to my top secret electronic lead screw prototype so I could control it with this rotary encoder. I can't tell you how amazing it felt to finally have it moving under its own steam, and that feeling lasted all of 90 seconds until I decided to test the backlash. At first it was looking great with about 40 microns of backlash at 200mm. That's just over 40 arc seconds. Unfortunately, this number proved to be pretty variable, and depending on the absolute position of the spindle, I was getting up to 5 times as much backlash. This is almost certainly down to roundness error in both the cycloids and the roller seats. But hey, less than 4 arc minutes of backlash is pretty damn good, and I discovered another potential issue that's going to be a hell of a lot easier to fix. In positions where the backlash is greatest, the cycloids obviously have a looser engagement with the rollers, and so it's possible to backdrive the gearbox. Combine that with this very cheap and very flexible coupler, and I'm certain it'll cause a bit of a false reading. But that's going to have to wait until the next video, when I hopefully even make some parts with it.